Welcome to Easy BTech. I'm Dr. Gayatri. Today I'm going to teach you about de Broglie's hypothesis of matter waves. And this concept we will be calculating with de Broglie wavelength. We will also find out what is the de Broglie wavelength associated with an electron. Louis de Broglie was a famous scientist who has proposed that matter also possesses dual nature like light. Matter is also possessing dual nature. That means it also exhibits particle nature as well as wave nature. This has been proved theoretically in a mathematical way by de Broglie. So now we will look at it how it happens. Electromagnetic waves. These waves, electromagnetic waves, behave like particles. Their behavior is like particles. And when I say here particles like electrons which are present, they behave like matter waves. These particles are going to behave like matter waves. These matter waves are called as de Broglie matter waves. Now, de Broglie was a scientist who has extended the dual nature to all the microparticles, to all the material particles like electron, proton, or neutron. According to de Broglie, whenever we are having particles to be accelerated, whenever particles are moving or made to move, particles are made to move or moving or accelerated, then we have a wave to be generated. That is known for us. The disturbance created in a medium is nothing but making the particles to move, which will be generating you a wave. So whenever the particles are accelerated, what will happen? We have a wave. We will be observing a wave. So whenever you have a wave, it has a wavelength. So a mathematical relation was extended to support his hypothesis. According to Planck's energy is given as h mu, where h represents Planck's constant and mu represents frequency of radiation. So you are having mu to be written as c by lambda. So expression becomes E equal to hc by lambda. Number it as 1. According to Einstein, the same expression of energy is given as mc square, where m represents mass of the particle and c represents the velocity of the particle. So I can have here your E equal to mc square to be numbered as expression 2. So I have here hc by lambda to be equal to mc square. Now what will happen? I have 1c to be cancelled. Then I'll be having lambda equal to h by mc, which is nothing but h by mv, nothing but h by momentum. H by momentum, because mass into velocity represents momentum. So it has become h by p. So this is your de Broglie's wavelength. The same de Broglie wavelength could be expressed in terms of kinetic energy, and we can also determine how much is the wavelength associated with it. So I'll once again write the equation lambda equal to h by m into c to be equal to h by p, representing de Broglie's wavelength. But remember, you are having m to be the relativistic mass, which is given by m naught by root of 1 minus v square by c square. This is one way of expressing de Broglie's wavelength. Now we will express same de Broglie's wavelength in terms of kinetic energy. So let's look at the second case. Lambda in terms of kinetic energy. Suppose E is representing you the kinetic energy. E is representing kinetic energy. as we said, we'll have a wave to be generated only when a particle is accelerated. So when a particle is accelerated, that means when the particle is moving, it has certain velocity. Suppose that v is that velocity. Then kinetic energy is given as half mv square. So the same expression could be expressed in terms of momentum, for which I need to multiply and divide the expression by m. Then it becomes p square by 2m. So from here I have E is equal to p square by 2m, where p can be rewritten for root of 2m into E. So in the last case, equation 3, we have seen that lambda is equal to h by p, where p represents momentum. Now I can write the same expression as h by root of 2me. This is another way. So now we can express here the same de Broglie's wavelength in another way. That is nothing but having de Broglie wavelength in terms of wavelength associated with electron. How much wavelength is associated with electron? We'll have this in terms of potential energy. Okay, we have been saying that a particle is accelerated, so wave is generated. So when do you have a particle to be accelerated? When we apply some external energy. Say that you have given here, applied here a potential. Applied potential. Let this potential be capital V. Whenever you are applying here this potential capital V, then you will be having wavelength to be associated with the electron, and that is determined now. So when this potential is given, what is happening? Electron is moving, electron is accelerating. So when electron is moving, it has velocity. So consider that velocity as small v like previous case. Okay. So now here we will have this kinetic energy half mv square to be equal to E into capital V. What is this V? It is representing your potential. Since you are having here electron to be accelerated, I have taken the charge of that electron as E. So you are having half mv square is equal to EV. From this expression, V, the velocity will be equal to root of 2E into capital V by small m, the mass. Now, we also had lambda equal to h by mv with our de Broglie's relation. So I'm rewriting this as h by m into 1 by v. So the same thing could be written as, because you know that the velocity is represented as root of 2 ev by m, it becomes m by root of 2 ev. So this is what you are having here. Lambda equal to h by m into 1 by v. In place of 1 by v, I am writing it as m by root of 2ev. So now the same expression I'll rewrite here, h into, taking m also inside, this outside letter m is taken inside, so it becomes inside in the sense inside the square root, 2m square ev. So what will happen? This m and square will be cancelled. So what will be left for us now? H by root of 2m ev. So what is our de Broglie's wavelength now? The de Broglie's wavelength is given as h by root of, as I said, this V is going to represent you with potential. H represents the Planck's constant, M represents the mass of the particle, mass of an electron or any other particle that has been considered, and the E as a charge on it. If we consider for electron, we know that H represents Planck's constant, which has a fixed value of 6.62 into 10 power minus 34. I'll write the value. divided by, since for electron, I'll also have the mass of electron as 9.1 into 10 power minus 31, and E representing me the charge 1.6 into 10 power minus 19, and I also have voltage capital V to be represented here. Then if I calculate this expression, this whole expression when calculated gives us 12.26 by root V Armstrong units. Don't forget, V represents your voltage. This is capital V, which is going to represent voltage. Because of this voltage, your particle has been accelerated. So how much is the wavelength associated with a moving electron? It is by 12.26 by root V Armstrong units. So you can have here a numericals to be based upon these three formulas that we have learned. One is lambda equal to h by momentum, which is nothing but h by p. The second one you have is lambda equal to h by root of 2 me. The third one you have is lambda to be written as 12.26 by root V Armstrong units. So these are the three important formulas of de Broglie's wavelength. If we are having this, we can have any sort of numericals based upon your momentum or voltage to be given to be solved. So we will generally have numericals to be obtained from this concept using your de Broglie's wavelength of h by Pe or h by root of 2 me or 12.26 by root V Armstrong units, where capital V represents voltage. Hope the learning from Easy BTech is making your learning more comfort and easy. So like, subscribe and share to Easy BTech. Thank you.